Good morning, everybody. I hope I don't have to explain my company. In case nobody knows, Freescale is the former semiconductor arm of Motorola. I hope that explains it. I was tasked here to describe a little bit the verification challenges my group, and in reality also a big portion of my company currently have. Jumping immediately to the first one. This is very much influenced from the fact that my last design, and actually a lot of designs we're doing in the near future, are actual designs done for the functional safety area, which means we have to work with all these ISO 26262 requirements. Harry already mentioned about all the requirements, tracking stuff, all the metric stuff. This is in the standard. You cannot release a design without doing all that kind of work. And as a fact, we have to do it. And all the metrics have to be done. And when you really boil down all this stuff, there is one stuff that comes up very hard to us, and that is actually the timing constraints and the synthesis constraints. If you think about, we have our big, great RTL, and we are verifying it to death. But all the timing requirements we are basically capturing with these constraints, we don't verify. We have our great STA. The constraints describe exceptions, they describe rules. We verify it with the STA, but do we verify the constraints? No. We have to review them. Same as if you have some mistake in your synthesis constraints, and usually they are reused for, say, time analysis. This is a self-fulfilling prophecy. So what, of course, you can do, and what, of course, we did is, we are doing our great level simulations, and we hope that the coverage done by them is good enough. And of course, you have to look whether all the exceptions you code into your timing constraints are covered by them. But do we know? No. There is no coverage that can say, okay, you covered that synthesis constraint, or you covered that timing constraint. Next thing is, the ISO 26262 basically says you cannot trust your tools. Every tool requires a second tool that verifies that the first tool works right. Actually, our last design got certified by that standard by an external company, so we managed it. But in reality, if you look at it, you have your gate level simulation as the only check. Actually, we found an error here. One single error. Do we know whether it's enough? Do we have coverage that says you found, you captured, you verified all your timing constraints? No, it's not there. So this is something that I definitely would like to see academia and EDA work on. I just don't see it yet. So if Harry has something here, it would be great. If somebody else has something here, please come to me. I would like to learn about it. So just to finish up this challenge, only verification currently reviews. We have one area where we just do reviews. We have power, UPF, CPF, can be checked together with RTL. We have RTL, myriads of verification languages, but here this is standalone. Next challenge. This is actually interesting that I heard that by also my two former speakers. In a little bit different nuisance, in a little bit different way of saying, but it seems to be a real challenge because all of us have that. How do we really identify? Okay, yes. How do we really verify that we covered everything? We have a diverse company. We have people in India. We have people in China. We have people in Brazil. They are doing IP verification. We are an SSC team. We do SSC verification. Of course, we have this unified coverage stuff. This works for normal RTL, but we have IP that has myriads of parameters. did we verify the actual parameter set, which is a requirement by the safety standard, by the way. So we have to check whether the actual parameter set is verified on the IP level and on the SOC level, and we have to combine the coverage databases. The one is located in India, the other one is located in Brazil, ours is located in Munich. This is not fun. Next area is if you need to combine that with the more advanced verification technologies, formal verification, what it actually means if I have a combination of formal verified IP block together with a simulation of that IP block, which is done randomized and so on. You have to make that up for your own. So here it would be really helpful to have a little better understanding of what it means to combine those things, what it means to really verify the portion you have to verify. Like Harry said, you not want to verify too much. I as an SOC team don't want to look into that. How to combine that with even more advanced things like AMS simulations, structural analysis things, and so on and so on. Coming to the third one, there's a lot of disconnected viewpoints. A lot of the areas we really see as a problem is having some first start of checks. We have AMS, analog mixed signal, can help you to verify a reset phase, can help you to verify some mode, specific modes, analog features of that. It really gets interesting when you have to switch modes. During this mode switch, what happens? You have to have really a full chip simulation with all stuff running in mixed signal. It's not going to work. Not this century, we will finish. Same thing is static timing analysis. Great tool. Problem is, it's static. So you define one mode, run your static timing analysis, you run the second mode, where you define a second mode, run your static timing analysis. As soon as you do your mode switch, is the timing still settled? SDA doesn't tell you. In our case, we have devices that have even more modes because all this safety stuff has internal test modes, self-test, memory-based, we even have application self-tests. The issue is if we have this great amount of modes, this large amount of modes, it really makes this problem much more complicated than if you have your usual device. Another area is these analog aspects. What we've seen is that you can get great analog behavioral models. They're usually written by the analog designers, and they tell us this is what the analog piece does. If you want to use it for verification, it's useless. As a verification guy, I want to see an analog behavioral model that tells me you cannot switch on this power line before the other one, or you have to run this enable pin 3 cycles before the third one. Analog people don't think about that. This is a domain problem, actually, because you have people who come from different domains and they think different. The only way to really start solving these things is let them work together, let them interact. So this is the third big challenge, and I hope I make the time. Thanks a lot.